542, more problems like you did on 5-4 day 1. They just get a little harder today. So, and I've got it set up to where each homework assignment goes along with the problems that we're doing that day of notes. So I'm not guaranteeing that every problem you encounter in homework we covered in the notes. Like, you should get to a point where you can do some of these on your own without me showing you exactly step by step how to do that particular type of problem. So here we go. We are going to start with a sheet of 10. Okay, it's a rectangle. So we've got a rectangular sheet of 10. I'm going to draw it on my paper. Here's a rectangle. And it is currently 25 by 20. Okay, it's a flat sheet of 10. We're going to turn it into an open box. And what we're going to do is we're going to cut squares out of each corner. Squares out of each corner. We don't know how big the squares are going to be yet. So let's make them that big, and let's call them X by X. So same size in this corner, same size in this corner, as best as you can, and same size in this corner. Now, I hope you can kind of like see what's going to happen here. Those corners are going to get cut out. And we're going to take the remaining piece. So I cut out corners. I'm going to throw them away. Right? Can you see that? Kind of. There we go. So this is what the new shape looks like with each corner cut out. And what I'm going to do is I'm going to take this strip and I'm going to fold it. Like that. I'm going to fold this one, and this one, and this one. Now look what I've got. I've got like a little box. See? Open top box. By cutting out the corners, then I folded this flap up, and I folded this flap up, and this flap up, and this flap up, and this is what I've got. Okay, so, got that. How large should the squares be? Okay, so obviously we're trying to find X. How large should the squares be? We want to make the box hold as much as possible. That's obviously what we're trying to maximize. We want it to hold as much as possible. We want it to have the largest area? No. Length? No. We want it to hold as much as possible. We want it to have the maximum volume. We're going to maximize volume. All right, let's get a volume equation. Ready? To find the volume of a box, you're going to take its length times its width times its height. Now, we started with a length of 25, but that's not the length anymore. We cut out some here on this side and here on this side. So I think my new length, length times width times height. I think my new length is the original 25 brought in x and x. 25 minus 2x. I think that's my new length. Width used to be 20. Well, we've decreased it by x on this side and x on this side. So my width is now 20 minus 2x. How tall is the box? Well, its height is the amount that we cut out. So its height is x. Now look, this is what we're trying to maximize. This is what we need to take the derivative of. Well, shoot, it's already in one variable. Woohoo! But it's a mess right now because you've got three things multiplied together and nobody wants to do a product rule with three pieces being multiplied together. So I suggest you FOIL out these two and distribute in your x. Here's what you get when you do that. FOIL them out, distribute in your x. I got 500x minus 90x squared plus 4x cubed. And at that point, I was totally ready to do a derivative. So I've got the derivative of volume with respect to x, my variable. And, set equal to 0. It's a quadratic. I know my numbers were kind of big, but man, I was pretty insistent that I wanted to factor this because I'm not a fan of the quadratic formula. I love factoring. So I was like, well, shoot, 12 doesn't go into everything, but 4 does. So I pulled out a 4. I tried to factor it. It didn't work. So I used the quadratic formula. I used the quadratic formula and I got two values of x. I got x is approximately 3.681 and x is approximately 11.317. All right, I'm either going to cut in squares on each corner 3.7-ish by 3.7-ish or 11.3-ish by 11.3-ish, whichever you decide. Pick one you like best, or maybe they both work. Man, I wish you all were in front of me right now. Well, if you choose this one, you've got a slight problem because if this length is 20 and you cut in 11 here and 11 here, that's not going to work. So we can rule out this one. It has to be this one. So the question said, how large should the squares be? Got it. Squares should be 3.68 by 3.68. And what is the area? No. What is the volume? So you've got to take this number and plug it in here, here, and here to get volume. Okay, I did that. I got the volume to be about 820.528. Here we go. All right, next one. We have got a cylinder that holds oil. It's a cylindrical oil can. What are the dimensions for the least material? Okay, so think about this. The dimensions of a cylinder, you've got radius going on and you've got height going on. Those are the dimensions of a cylinder. we would look at its radius and its height. That's what needs to be established. So, find the dimensions. Okay, we got that. We want to use the least material. This is kind of tricky. It doesn't say we want it to hold a small amount. That would be volume. We want it to, all the material that it takes to make it, all the wraparound material and the bottom and the top, that's what we want to be minimized. That's surface area. Least material. So we are going to minimize surface area. Okay, well let's get an equation for surface area then. Surface area equals, let's start with the easy ones. Let's do the bottom and the top. They're circles. There are two of them. Right? Because there's a bottom and a top. Plus, now we need to consider the wraparound part. Well, if you take a cylinder, and you cut it down the side and you unroll the cylinder, all you have is a rectangle. You've got the length of the rectangle and the width of the rectangle. Well, the width of your rectangle is just the height of your cylinder. The length of your rectangle is the circumference of your cylinder. So, excuse me, this is the height. This is circumference, 2 pi r. 2 pi r h. That's surface area. That's what we need to take the derivative of. If you want to try to take the derivative right now, you got the derivative of surface area with respect to, oh, I don't know, r or h, not sure. You need another equation. We need another equation over here that's going to help us make a substitution down to one variable. So, the only other information in the problem is that it holds 1 liter of oil. It holds 1 liter of oil. I had to cheat a little bit. I was like, oh, I know that's a volume measurement. I know that's a volume measurement. But 1 liter, I need to get this to like radius and height. I need to get this to linear measurements. I need all my measurements to be linear measurements, like inches or centimeters or whatever. So I cheated a little bit. 1 liter was 1,000 cubic centimeters. And from there, I was like, okay, there's my linear measurement. So now I can make a volume equation. Volume equals the area of the base, pi r squared. So volume, the area of the base, over and over and over and over and over and over again. So I'm going to take that times the height. We know that the volume that it holds is 1,000 cubic centimeters. Totally got that online. Some of you in I guess chemistry maybe? Physics? I don't know. Some of you just know this right off the top of your head. I did not. So here's my volume equation. This is how much it's going to hold. I know it's going to hold this much. I want to minimize surface area. So I think what I would do, this is easiest to solve for h, not r. So I'm going to solve this for h. and I'm going to come over here and sub it in my surface area equation. Now our surface area is down to one variable. That's good, but it is a mess. We totally want to simplify that before doing a derivative. So let's see, 2,000 pi is gone over r. Not bad. Not bad. Not bad. Let's do a derivative. The derivative of surface area and r is my variable. Remember, pi is just a constant. This becomes 4 pi r. This is 2,000 r to the negative 1. So I'm going to bring my negative 1 down. I get minus 2,000 over r squared. Set that equal to 0. I think what I'm going to do is I'm going to, let's see. Yeah, I'm going to move this over and cross multiply. $2,000 divided by 4 is 500. The cube root of 500 over pi. Oh, that's ugly. Okay, so on my calculator, I got r to be approximately, I did that on my calculator, I got 5.419-ish. And my height was 10.839. Those are the dimensions of a cylinder that will use the least material. And it only asks for dimensions. It doesn't say, and go ahead and find the, whatever, it doesn't say that. Okay, last one. We want to, if we're a business owner, we want to maximize profit. So here's what we've got going on. Our revenue function is this. Revenue is all the money we take in. However, we don't get to keep all that money. We've got costs that we have to spend money on. So we have to spend money on our employees. We have to spend money on insurance, the building, whether we're leasing it or paying off a mortgage or whatever. We got the building, we got the utilities on the building. There's all kinds of costs involved in running a business. So, but as a business owner, raking in money is no good if we're spending money like crazy, okay? So profit is that sweet balance between revenue and cost. Profit is how much do I have after everything is brought in and everything's paid out. That's profit. So that's what we're wanting to maximize. We want to maximize profit. Well, it says that. There's no need to rewrite it. We need a profit equation. So profit equals revenue minus cost. It's pretty easy. There's my profit equation. That's what I want to maximize, so let's do a derivative. Now, since this is written in function notation, I will allow you to write p prime. And I get negative 3x squared unfortunately, oh, hold on. I forgot to set equal to 0. 0 equals, and I tried to factor it. It doesn't factor. So, quadratic formula, 2 results. I got 3.414, 3.414, and I got 0.586. All right, 2 answers. What on earth do they mean? So let me go back up to the problem. X represents thousands of units. Okay, that makes sense. Thousands of units. So here's what I want to produce. I either want to produce 3,414 units or 586 units. One of those is going to maximize profit. Which one? Which one of these X values will maximize profit? There are 3 ways that are like valid ways to look at this problem. 3 ways to choose which X to use. One way is to do a sign chart on P prime. So put like 0.5-ish there, put 3 there, plug in 0 to profit, you get negative 6. Plug in like 2 and you get, negative times negative is a positive. Plug in like something absurd to make it easy, like 100. 100, that's going to be positive, that's going to be negative. Aha, look. Negative slope, negative slope, negative slope, 0, positive, positive, positive. That's not the one we want. Positive slope, 0, negative slope, negative slope. That's the one we want. That's the one that'll maximize profit. Another way that you might have thought of, or maybe you didn't, is try them both. Which X value gives you the highest profit? Plug them in. Plug 3.414 into profit and plug 0.586 into profit and see which one gives you the highest profit. And the third way is, go back up to your profit equation. See the profit equation? Profit equals negative leading coefficient on a cubic. You know the end behavior for negative leading coefficient on a cubic. Your profit function looks kind of like this. So the first critical value that we're going to come to is a minimum. We don't want that. The next critical value that you come to is a local maximum. That's what you want. So any one of those lines of thinking would be an excellent choice for an excellent way to choose which answer you want. So is there a production? Yes. 3,414 somethings units.